Welcome to the video lecture series. Today, in the subject engineering mechanics, we are going to discuss friction on inclined planes. In this topic, we are going to solve a problem on connected bodies resting on inclined planes. Two planes AC and BC inclined at 30 degrees, 60 degrees to the horizontal, meeting at point C. Two bodies, one is 1000 newtons resting on plane BC and it is tied by a rope and connected to another body which is resting on plane AC whose weight is W newtons. The quotient of friction between plane BC and 1000 Newton block is 0.25 and the quotient of friction between AC and W Newton block is 0.20. Now find the least value of W and greatest value of W. Here we have two cases. One is least value of W and greatest value of W. We need to find W value two times. These are two different cases. For the same given data, what is the least value of W and what is the maximum value of W to keep the body in this position, in the equilibrium position like this. For the first case, to find the least value of W, for the least value of W, it is assumed that the W Newton block is moving upwards. That means the 1000 Newton block is dominating and it is pulling the W Newton block upwards. The 1000 Newton block direction is downwards, or the 1000 Newton block is tending to move in the downward direction, so that W motion or W will be tending to move in the upward direction. So that is the least value. That is the least value. If the W value is further decreased, the body starts moving, the system starts moving downwards. 1000 Newton block moving downwards. That is the least position of static equilibrium. That is what least value of W. Now, for the greatest value of W, at this condition, the tendency of the W Newton block is to move downwards. That means the W Newton block is dominating and its motion, the system is moving in such a way that the W Newton block which is resting on AC will move in the downward direction and 1000 Newton block start moving along with it in upward direction. That means for the greatest value of static equilibrium, if you further increase W value, the body will move to dynamics case because the body starts moving in the downward direction. Now find out two values of W which will keep the body under equilibrium. That means between least to greatest value of W, the body will be under equilibrium. It is not a single weight or single value of weight which keeps the body under equilibrium. No, the body will be under equilibrium between a range of values of W. For between least value of W to greatest value of W. If the weight increase further, the system will lose static equilibrium and the W Newton block moves downwards. and if you further reduce the value of W below its least value, then the body starts moving, the system will move in such a way that the 1000 Newton block will move downwards and W will move along with it in upward direction. In between least value of W and greatest value of W, the body will be at static equilibrium. Now, in this problem, we are going to find the least and greatest values of W, which will keep the system under equilibrium. First case, for the least value of W, draw the free body diagram of 1000 Newton block. Draw the free body diagram of 1000 Newton block and W Newton block separately and apply the static equilibrium conditions. So for that, first draw the free body diagram of 1000 Newton block. The 1000 Newton block is resting on plane which is at an angle of 30 degrees. The weight always acts vertically downwards, and the normal reaction will be always perpendicular to the contact surface. Here the contact surface is at an angle of 30 degrees to the horizontal, and normal reaction N1 is perpendicular to that. Now, the tension in the string. The two bodies are connected by a string. Now I am assuming the bodies are connected and passing over a frictionless pulley, and the string is weightless. Under these assumptions, the tension in the string is T. For the least value of W, the 1000 Newton block is tending to move in the downward direction. Therefore, the friction at the contact surface F1 will be in upward direction. This is the free body diagram. Now draw the force diagram. Remove the body and remove the supports and replace only the forces. Weight always acts vertically downwards, and normal reaction is acting at an angle of 30 degrees to the vertical or 30 degrees to the weight. Let us find the angle made by the normal reaction with vertical or with weight. For that, I am going back to the free body diagram. This is what the direction of N1. Now here the angle is 30 degrees. We know that the normal reaction will be always perpendicular to the contact surface. The angle between normal reaction and contact surface, that is nothing but the plane, is 90 degrees. Now draw a vertical line here. Draw a vertical line. See here. Now we got a right angle triangle, this one. Here the angle made by the plane with horizontal is 30 degrees and normal reaction is making an angle of 90 degrees. So here the angle made by the normal reaction with horizontal will be 60 degrees because the total angle in a triangle is 180. Now using this another triangle, see, draw a vertical line here. Now this is a vertical line, or it is the direction of weight, which is making 90 degrees with the horizontal, and here the angle is 60 and the remaining angle in this triangle is 30 degrees. That means the normal reaction is making an angle of 30 degrees with the vertical, or otherwise normal reaction will be making an angle of 30 degrees with the weight, or we can simply take it as the angle between normal reaction and weight will be always equal to the angle between plane and horizontal. Now, after knowing the direction of N1 is making an angle of 30 degrees to the vertical. Now, F1 is acting along the plane and tension in the string is also in the same direction of friction. Now, apply the static equilibrium equations. sum of all forces parallel to plane equal to 0. Here in this case we are not resolving the forces into horizontal components and vertical component. Why? Because if we resolve the forces into horizontal component and vertical component, only one force, that is 1000 newtons, is in vertical direction. All other forces are making some angle with horizontal or vertical. Okay, we need to resolve n1 into two components, n1 horizontal component as well as n1 vertical component. Similarly, f1 horizontal component, f1 vertical component, t1 horizontal component and t vertical component. We need to resolve all the forces. Instead of that, if we resolve the forces parallel to plane and perpendicular to plane, we can resolve the forces into any two mutually perpendicular planes. In this problem, we are resolving forces into two mutually perpendicular planes. Those are, one is parallel to plane, other one is perpendicular to plane. The advantage is, see here, if we resolve the forces parallel to plane, T1 and F1 are in the direction of plane, in the same direction of plane, and N1 is normal to the plane. And if we resolve normal to the plane, perpendicular to the plane, we will consider N1 only, and F1 and T will not contribute to that. And only one force is there which is making an angle with the plane, that is weight. If we take this advantage, we need to resolve only 1000 Newton force, not all the forces. That's why we'll resolve the forces parallel to plane and equate it to 0, because the system is under equilibrium. The equations are 1000 sine 30, that is, if you resolve 1000 newtons weight, it's along the plane component or parallel to plane component is 1000 sine 30, and its perpendicular to plane component is in the downward direction opposite to n1, and its value is 1000 cos 30. See now, all the forces are either along the plane or normal to the plane. Now taking the forces which are acting parallel to plane or along the plane are 1000 sine 30. The body is tending to move in the downward direction, that's why I am taking 1000 sine 30 positive, 1000 sine 30 minus t minus f1 is equal to 0. Only three forces are acting parallel to plane. Now t is given by 1000 sine 30 minus f1. From the above equation, t is equal to 1000 sine 30 minus f1. Now resolve the forces perpendicular to plane and equate it to 0, because sum of all components of forces which are perpendicular to plane will balance themselves, and final effect should be 0, because the body is under equilibrium. Now perpendicular to plane we have only two components or two forces. One is n1, which is acting in upward direction perpendicular to plane, and 1000 cos 30 acting in downward direction perpendicular to the plane. N1 minus 1000 cos 30 is equal to 0. I am assuming N1 positive, and opposite side automatically it will be negative. N1 minus 1000 cos 30 equal to 0. N1 is equal to 1000 cos 30, which is equal to 866.03. Now we know that the quotient of friction is equal to limiting friction by normal reaction. The equation for finding quotient of friction is limiting friction by normal reaction. Substituting the values for this condition, F1 friction at the contact surface of 1000 Newton block and plane is equal to mu quotient of friction into normal reaction. So from this equation we can find the friction value. Friction is given by mu is 0.28, and N1 normal reaction is 866.03. Now substitute this F value back into the equation of T, back into the equation of T. Substitute the value of F1 in the equation 1. This is equation 1. To find the value of tension in the string. So T is equal to 1000 sin 30 minus F1. F1 is 242.49. So that we'll get the tension in the string, which is 257.51 newtons. Now, by considering the free body diagram of 1000 Newton block and resolving the forces and equating to 0 or applying static equilibrium equations, we got friction at the contact surface and tension in the string. By taking these two values, let us move forward to solve the least value of W. In the second case, draw the free body diagram of W Newton block. This is the W Newton block which is resting on a plane which is making an angle of 60 degrees to the horizontal. Weight always acts vertically downwards. Weight is unknown and we are going to find its value. Normal reaction N2 will be always perpendicular to the contact surface. Tension in the string is T. Now the body is assumed to move upwards because we have considered the 1000 Newton block is moving downwards for the least value of W. That's why the friction at the contact surface F2 will be in the downward direction. Now draw the force diagram. Weight always acts vertically downwards. Normal reaction will be perpendicular to the contact surface. That means 60 degrees to the vertical. And tension in the string is 257.51, which is acting in upward direction, and friction F2 is acting in the downward direction. Now resolve the forces parallel to plane and equate to the 0. Forces parallel to plane equal to 0. Here the body is moving in upward direction, that's why I am assuming T is positive and F2 is negative. T minus F2 minus W sin 30. The W sin 30 is the weight component W sin 60, weight component parallel to plane, and weight component normal to plane is W cos 60. The weight W is resolved into two mutually perpendicular components. One is parallel to plane component, other one is perpendicular to plane component. W sin 60 is in the downward direction. T minus F2 minus W sin 60 is equal to 0. T value I am substituting here. F2 I need to find, and W sin 60 I am considering it as equation number 2. Now find the forces perpendicular to plane and equate it to 0. N2 minus W cos 60 equal to 0. Perpendicular to plane we have only two forces. One is N2, other one is W cos 60. For the equilibrium of the system or for the equilibrium of the body, if two forces acting on the body, then they must be equal and opposite. That's why N2 is equal to W cos 60. W cos 60, which is equal to 0.5 W. We don't know the value of W. So cos 60 equal to 0.5. N2 is equal to 0.5 W. Next, we know the equation for quotient of friction. Mu is equal to F by N, and substituting for this condition, F2 friction at the contact surface between the W Newton block and the plane is F2 is equal to mu N2. Substituting the values, calculate F2 value. F2 is equal to, the quotient of friction is 0.2 here. For this block and the plane, the quotient of friction is given as 0.2 into N2 is 0.5 W, which is equal to 0.1 W. Friction value in W is 0.1 W. Now substitute this F2 value back into the equation 2 to find the unknown value of W. So this is equation number 2, 257.51 minus F2 W sin 60 equals 0. Now substitute F2 value here. 257.51 minus 0.1 W minus 0.866 W equal to 0. By solving this equation, we can find the value of W. W is equal to 266.57 newtons. 266.57 newtons. This is the least value of W, because if you reduce the value of W further, the system starts moving and the 1000 Newton block will move downwards and the W starts moving in the upward direction. Above this, the body will be in equilibrium. Now let us find the greatest value of W. For the greatest value of W, again consider the free body diagram of 1000 Newton block and W Newton block separately, and apply static equilibrium equation for both the bodies, so that we can find the value of W, the greatest value of W. Only thing we need to consider here is, for the greatest value, the W Newton block is tending to move in downward direction and 1000 Newton block will be moving in upward direction. That is the only change. By changing this direction of motion, we can find the greatest value. Let us look at this. Draw the free body diagram again. The 1000 Newton block is resting on the plane. Weight always acts vertically downwards. Normal reaction will be always perpendicular to the contact surface, and the tension in the string is parallel to the plane. And the friction here, in this case, the 1000 Newton block is tending to move in upward direction at the greatest value of W. At the greatest value of W, W is tending to move in the downward direction and 1000 Newton block is tending to move in upward direction. If you check the previous problem or previous case, for the least value of W, we have considered the 1000 Newton is dominating and it is trying to move in the downward direction. Now the body is tending to move in upward direction, friction will be in opposite direction. This change, we can find the greatest value. Draw the force diagram. 1000 Newton block. 1000 Newtons weight always acts vertically downwards. Normal reaction will be always perpendicular to contact surface. The angle between normal reaction and weight is nothing but the angle of the plane, 30 degrees. We have seen in the previous case how to calculate it. The friction is acting in the downward direction and tension is acting in the upward direction parallel to the plane. Now, take the equations, static equilibrium equations. Sum of forces parallel to plane is equal to 0. Find out the forces which are acting parallel to plane and equate the sum of them to 0. Here, T1 is acting parallel to plane in upward direction. F1 is acting parallel to plane in the downward direction, and the component of weight, that is 1000 sin 60, is acting parallel to plane in the downward direction. 1000 cos 60 is the weight component which is perpendicular to the plane and acting in the downward direction. Now, three forces are acting along the plane: tension in the string, friction, and weight component. Now take the equations. 1000 sin 30 minus T minus F1 equal to 0. T is equal to 1000 sin 30 plus F1. Now take the forces perpendicular to plane and equate their sum to 0, because the body is under equilibrium. Now N1 minus 1000 cos 30 is equal to 0. N1 is equal to 866.03 Newton. And find out F1 value by using equation, quotient of friction equation. mu is equal to mu is equal to F by N. So from this equation calculate F1 value. F1 is equal to 242.49, and substituting this F1 value in the equation 1, T is equal to, we can get the T value here, T is equal to 742.49. T is equal to 742.49 newtons. Now consider the W Newton block and draw the free body diagram. Weight always acts vertically downwards. Normal reaction will be perpendicular to the contact surface. Tension in the string is parallel to the plane, and friction. Here in this case, the weight W Newton block is tending to move in the downward direction at its greatest value of W. Therefore, the friction will be upward. Draw the force diagram. Weight always acts vertically downwards. Normal reaction perpendicular to the plane, which is at 60 degrees to the vertical, and tension in the string is 742.49, and friction is F2. Right. Now apply static equilibrium equations once again. Forces acting parallel to plane is equal to 0. Parallel to plane, we have three forces. One is tension in the string, friction, and the weight component. If you resolve the weight into two mutually perpendicular components, W sine 30, W sine 60 is the component which is parallel to plane, and normal to plane, W cos 60. Now three forces are acting parallel to plane and two forces are acting perpendicular to plane. Now write the equations. W sin 60 minus T minus F2 equal to 0. W sin 60 minus 742.49 tension value minus F2 equal to 0. Now write the equation, second equation of static equilibrium. Sum of forces acting perpendicular to the plane is equal to 0. N2 minus W cos 60, N2 minus W cos 60 equal to 0. N2 equal to W cos 60, which is equal to 0.5 W. We know that mu is equal to F by N, friction by normal reaction equal to coefficient of friction. Using this relation, calculate F2 value. F2 is equal to 0.1 W. The quotient of friction between the W Newton block and the plane is given as 0.2 in the problem, and N2 we got 0.5 W. So F2 is equal to 0.1 W. Now substitute this F2 value in the equation number 2 to find the value of W. So this is the equation. Substitute F2 value, F2 equal 0.1 W. By solving this equation, so take all W's in one towards LHS and take the numerals to RHS and solve this equation. So we will get W is equal to 742.49 divided by 0.766, which is 969.30 newtons. This is the greatest value of W. In between the least and greatest values, the body will be under equilibrium. If you increase further, this is the greatest value of W, if you increase further, the body will not be under static equilibrium. The W Newton block starts moving in the downward direction. Thank you.